Our next speaker is Dan from Hawkeye360.
Can everybody hear me? Cool. I'm Dan CaJacob. I'm Director of Space Systems at Hawkeye360, and I'm here to talk about building a moderately complex modem with spare parts. Skip that. I won't dwell on this too much. So the goal of this work was to build basically something that closely models a CCSDS recommended implementation of a space-to-ground, ground-to-space modem, typically used with bigger satellites at higher data rates. Really wanted to support IP encapsulation, so I can use common Linux tools like SSH and rsync to talk back and forth between the spacecraft. Latency minimization was a high priority on this design. I've built things like this before with less complex systems. If you don't implement it correctly, you often cause a bunch of latency yourself in your own flow graph. So this was a big part of this work. The bonus was to add TCP acceleration via some performance-enhancing proxy magic. I don't think I'll talk about that today, but that was something that was done. So what is a moderately complex modem? It's kind of a joke, but in this case, it's a QPSK-based modem, and we're using concatenated coding. So there is depending on how you define it, I think there's an inner half-rate convolutional encoder and Viterbi decoder on the receive end, and then I'm also using Reed-Solomon encoding to handle bursts of errors that you typically get with a ground-to-space modem, and combining that with scrambling and interleaving. That's what really helps out with the burst errors. Like I said, it's basically the CCSDS recommendation without their insane higher-level framing protocols. So I'm mostly sticking to their file layer recommendations here, and then sort of doing my own thing at the higher level. A big thing I'll talk about is phase ambiguity issues. This was probably about half of the time I spent on this design was dealing with that. I'll talk about my simple IP encapsulation solution and things you could do that are better than that. Latency reduction, as I said, and I'm lazy. I don't like to write C++ code, so I try to do as much as possible in GRC. So spare parts, that kind of comes back to that last point, is I'm trying to do this as much as possible in GRC with existing blocks and avoiding writing my own blocks. I do fail at that, but I do pretty well, and I'll show you where we had to write a few custom blocks and use a few out-of-tree modules just to make things simpler. GNU Array is great because this is possible.
Hey,
Right?
hey Dan,
Yes,
your
sir.
video's flickering. I don't know if you...
Huh. That better?
Yes.
Okay. By the way, if, 10 minutes out before the end, if I'm rambling on and not doing a demo, somebody stop me. All right. So, and there's out-of-tree modules that I completely missed that might have helped me, like grmapper. I only found out about recently. So. Talk about some quick success. With GNU Radio, it was very easy to implement subsets of this whole modem. For example, I had no experience with convolutional codes. So I originally started using the CCSDS block and quickly proved that worked to some extent, and then quickly moved on to building modems that were using the FEC API, which is awesome. GNU Radio makes it easy to sort of work at whatever layer you want. So early on, I wasn't even modulating. I'm just putting symbols through the convolutional encoder and decoding them and verifying that they're the same. And then you can build your modem sort of layer by layer out from there. Using the stock ton block for the network interface, because like I said, I want this to be IP encapsulating. My early design, this is a continuous modem, so it's not bursty. So when I'm not transmitting, like user packets, I need to be putting some sort of filler in there. And early designs had that up front, and the latency was heinous, and I'll talk about how I fixed that. This early model did work, but not really, a usable solution. So here's like a high-level view of what the modem looks like. I've highlighted the stock blocks, which come with GNU Radio by default. Some OOTs that I used, higher blocks, and custom out-of-tree blocks that I wrote. So you can see, really, all I had to write myself was an IP encapsulator and decapsulator blocks. Those are dead simple Python blocks. Probably took 10 minutes to write. The frame insert was the nth version of 10 different versions, and I was putting that in different places in the flow graph. Ultimately, I'll talk about this more, but you want to put that right before the usurp. That's a C++ block and is also pretty dead simple. I owe a lot to, I think it's Andre Lafaldi, maybe getting the name wrong, but he has an out-of-tree module called GRCon17, which I hacked on a little bit. That does not do the convolutional encoding, but it does provide the Reed-Solomon encoder, the interleaver, and the scrambler. So I got that all in one block, and that made things really easy. Let's see. So starting to look at some of the internals of this modem. Like I said, I'm using convolutional encoding. CCSDS recommends a rate 1/2 constraint length 7 convolutional encoder. This modem relies on having memory, or this encoder relies on having memory, and adding the fill frame at the end, because of the way things are encoded, this memory becomes a problem, because it basically every bit you encode depends on the previous 12 bits. So when you're trying to match up things, it becomes difficult. I'll get more into the detail with that later. But there's in the CCSDS recommendation, there's sort of a frame, and that's preceded by a 32-byte sync word. It's called the ASM. I think it's the asynchronous marker or something like that. After convolution, that turns into 64 bits, since we're doubling the data rate here with rate 1/2. Because of that 12-bit memory, when you convolutionally encode that ASM, the first 12 bits are sort of indeterminate. You don't know what they'll be a priori, because it depends on the data that came before. But the bits after those 12 bits are all deterministic. If you pre-encode it, that's how it'll look in the data stream. And for simplicity, I chopped off the first 16 bits just so I could stick to byte boundaries. And I'm not using, CCSDS recommends inverting one of the polynomials. I'm not doing that, but Daniel Estevez, who has a great blog about a lot of these things, has recently made an update to GNU Radio that makes that possible. The Reed-Solomon encoder was, like I said, provided by, I think, Andreas Lafaldi. It's 255 bits, and 32 of those bits are parity symbols. CCSDS recommends an interleaving depth of 5, and like I said, we're also applying scrambling. And I believe we're using Phil Karn's implementation of Reed-Solomon here. And you can kind of see in that little description of the block there, early on, up front in the modem, I was inserting the idle frames like as soon as possible in the CCSDS encoder. That was a terrible idea, and I'll talk about that later, but it added a ton of latency to the point where doing IP transfers had a latency of like 20 seconds. So not great. Some of these other diagrams, I don't think the pointer shows up. Oh, it does, cool. This sort of shows, these are clips from CCSDS documents, which are, they suck, but they just show some of the optional coding schemes you can do, and we're doing them all. And here you can see this sync marker here is just, that's the ASM I was talking about. And then this shows the big Reed-Solomon code blocks and parity symbols. So here's the transmitter side of the modem. I've got a virtual source here, which I'll show where that connects later. We've got the CCSDS encoder block that is provided by Andreas Lafaldi. You've got to unpack the bits for the FEC extended encoder, which is there's an object not shown here that's setting all the parameters for the convolutional encoder. Then you got to repack your bits, send that through the Constellation modulator. I've got a Constellation object. Like I said, this is a QPSK modem. And then this block down here is one of the custom blocks I wrote that inserts idle frames, and that basically just it kicks out one CCSDS frame at a time. And if you don't have a complete CCSDS frame, if you're called with not enough work to send out a user CCSDS frame, it inserts an idle frame, which is just a bunch of zeros preceded by an ASM, which it's an encoded version of that. And that's going to the usurp. Here's the receiver, so that's kind of the opposite side of that. I'm using the RMS AGC block that Daniel Estevez recently put together. You can get away without it, but it helps the flow graph attains lock like a second faster, and it will probably work better across a bigger range of gains. Got the FL band edge filter here to get my frequency sync. I've got the polyphase clock sync, which is pretty awesome. CMA equalizer is magic and seems to help. And then I've got this kind of weird arrangement of two Costas loops and a correlation estimator. And I'll talk about that a little bit later, but basically it just helps you resolve the phase ambiguity issue with QPSK. There are better ways to do this, but I was lazy. And then we got the Constellation soft decoder, since I'm using soft symbols, and the Viterbi decoder, the CCSDS decoder, and then we're back to our sync. And here we see where those sinks and sources connect up. I've got a ton tap block right in the middle here. This allows me to connect basically a network interface to userland, which is the modem running GNU radio. And then I've got my encapsulation and decapsulation Python blocks to basically wrap the IP packets that are coming in and out of the chun tap, and then all that stuff goes to the modem. You can see, I hate these types of diagrams, but you can see sort of what this whole stack looks like, where I've got, ideally the user is working in TCP or IP, and then we're encapsulating the packets at the link layer. The file layer is CCSDS, and then we have an RF link connecting to a modem on the other side that's implementing a similar system. So ideally, the user just sees they're putting TCP or UDP. I should say I've messed this diagram up a little bit, but IP or UDP packets across this network. I also talk about a few custom parts, and that's basically just me writing my own blocks. We talked a little bit about this already. I spent a lot of time on the phase ambiguity issue. Derek Kawamoto helped me out with a lot with that. Settled on a compromise that actually didn't require me to write my own block, although I tried that beforehand. The fill frame insert is stupidly simple, but it's important to put it in the right place. I tried everything else before that, but the post-modulator convolutional encoder fill frame stitching is really important. We'll talk a little bit more about that. And I already talked about, I think, all of this. So I've said I really tried to avoid writing code. This is the comedy slide here. I went through all these stages of avoiding writing code, and finally knuckled down and did it. So getting into some of the problems and how we solved it. So latency reduction, basically add your fill frames at the end. GNU Radio has all sorts of buffers, and doesn't matter how you try to solve this. If you try to mess with GR buffer or GNU Radio buffer manipulation, that was my first approach. I've done stuff like this before, but ultimately what happens is if you try to add fill frames or fill bytes early in your flow graph and you have several buffers down, GNU Radio is going to fill up those buffers all the way from the sink. So you're going to have all this latency, because it's trying to feed your sink is your UHD block. And GRPerfMon is awesome for this. This really demonstrated it for me. I wish I could show it to you here, but basically I had this sea of red leading up to my idle frame generator, and that's where my 20 seconds of latency was coming from. So that was terrible, and I got great advice on IRC on how to fix that, and I finally did it. I also played after adding the fill frames at the end. Things were a lot better, but I played with other things to improve the latency too, including USB buffer manipulation. That didn't help a lot. I think that's already probably done pretty well. I tried playing with that. I think there's one last buffer between the last block and the UHD sync. I tried playing with that. That didn't seem to help much. Some smaller gains. You can tweak the amount of work that the convolutional or the convolutional encoder and decoder work on. That helped less than I thought it would, but it definitely hurts if you get it wrong. If you try to give it too small a chunk, if you think oh, that'll reduce latency, it doesn't help that much. Increasing the data rate is pretty free. And there's some significant latency that just comes from the length of the frame, because I'm always buffering at least one frame up. So even at 1 megasample per second to the radio, I've got a minimum of 41 milliseconds by my calcs. And these diagrams here from GRPerfMon, and this is just showing the buffer fullness of the whole flow graph. Over here you see this is connecting to the usurp sync, and you can't see it here, but it's really. This looks high compared to everything else, and it is, but I mean, I'm hardly filling this buffer at all. It's less than 1%. So adding the fill frames last, we were just talking about this. This sort of gives you a diagram of a stream of CCS/DS frames. So we've got the ASIM. I've got scrambled interleaved read-Solomon data here. This whole thing gets convolution encoded, this next layer, and you can see here if I ran out of data, I'll insert a fill frame there, and that also gets scrambled, interleaved, and a read-Solomon encoding applied to it. Now I talked about the real difficulty of this is that since I'm adding this frame at the end, it's much easier to add the fill frame before all the encoding, because then you can just add the raw frame and it gets encoded by GNU Radio. If you try to add at the end, it's going to help with your latency, but since it's a continuous modem, you have to stitch everything up so it's bit perfect. And since I'm doing convolutional encoding, there's memory, right? So I have to take a fill frame that's known, pre-encode, read-Solomon encode it, scramble it, et cetera. That's easy. But then convolutionally encode it, and 12 of those bits up front are dependent on the previous data bits, which you don't know since you're pre-encoding this. So you have to play this game where when you generate, you sort of add some data to the end of your data frame that you chop off, another ASIM, and then you stitch up your pre-encoded fill frame so that it looks like you knew the data all along. And you can do this, but I spent a long time getting this right, and I'll show a little bit of that. So this talks about building the fill frame. I've got a bunch of flow graphs that help me encode the ASIM and encode the fill frame, so I can give that to the fill frame inserter block. Fill frames are just a bunch of zeros. And a lot of the GNU Radio blocks that you use will have memory, so you have to adjust for that, not just the convolutional encoder, but you have to, if you want to get the exact output sequence that you're going to expect in a streaming modem, you need to flush some of these blocks with zeros ahead of time. So there's a bunch of work doing that. I'll pull these up in a minute. I also, as part of this, even building out all these flow graphs, I still wasn't able to stitch everything up quite perfectly, because since these blocks have memory, when you're looking at the output, you're not quite sure where things are supposed to actually start. And so Derek pressed me and helped me, and I finally hand encoded the ASM to help me match up my simulation with what the truth should have been. And that's what's shown here. That was tedious Saturday night fun. And then on the decoder side, to help with the phase ambiguity resolution, I'm building a correlation sequence based on the ASM, and this involves basically the other side of all this ASM encoding I was talking about already. It has memory issues, et cetera. This is just a view of the flow graph I'm running to encode the ASM, and then it's spitting out with the complex symbols that I can feed into the correlation estimator. So phase synchronization is, I've always dealt with lower level modems like GMSK or BPSK. So phase synchronization with QPSK is a lot harder. I had very early success where I had a modem that was working, but it was either only working half the time or 1/4 of the time when you fired it up, right? Because it's locking on to the wrong constellation pattern. So there was some work to get that right. I was given good advice on how to do this. I tried, I failed, and Derek taught me a neat little trick on how to deal with this, which is basically using 2 Costas loops. So you see here I've got the polyphase clock sync with CMA equalizer. We've got the first Costas loop to do some phase synchronization. And then on the output of that, I've got a correlation estimator, which is looking at that encoded ASIM. So that ASIM precedes every it's a known sync word. It precedes every CCSDS frame. So I'm getting a correlation peak, looking for that ASIM marker. And then the results of that are being fed downstream to the secondary Costas loop, which resolves the remaining phase ambiguity if there is any. So now when I fire up the modem, at least when I'm not on stage, it always works. Let's see, yeah. And there are better ways to do this. This is some documents, some pseudo-helpful documents from the CCSDS documentation that shows you the myriad ways to phase synchronize your modem. I'm basically doing this one. I spent a lot of time on this tree because I've typically built modems that had differential encoding in the past. I had some success with this, but in the end, this was the most reliable, is using the unique word detection technique. This sort of shows based on carrier phase error, you could have IQ inversion, flipping, or an even inversion. And it seems like what I'm doing is the most recommended technique. It's also one of the more complex ones for the modem. So in reality, I'm sure all modern CCSDS modems probably do this, but I'm sure the old ones didn't. So my IP encapsulation blocks are pretty simple. I waited sort of till near the end to add this. Before I was just like streaming through the complete works of Shakespeare, which you can get from the Gutenberg project. So I built a toy implementation for this with dead simple Python blocks. I've got a 2-byte header that just defines the length of the encapsulated or the IP packet to follow, and the rest is just fill data. So really, I'm only allowing 1 IP frame per CCSDS frame right now. A better way to do this is use HDLC or some other sort of byte delimiting protocol. Do I need? Okay. Yeah, and so you can see how this structure resolves here. I will get into the demos here. All right. So I've got a couple of flow graphs here that help me build up the modem flow graph. So there's the ASM generator block. So this is taking the raw ASM and convolutionally encoding it. And you can see the results here, and basically I can just copy off these encoded symbols and put them in my, my main flow graph. The ASM post-Costas flow graph helps me build my, my correlation pattern that I feed to the correlation estimator. So this is the encoded ASIM modulated, and so that we can correlate right onto that on the receive stream. And then likewise, I can just copy this off and put it into the larger flow graph. And then the idle frame encoder is another subset of this modem where I'm generating an idle frame sequence, and again, I can just copy that off and put it into the flow graph, into the idle frame inserter. And all three of these flow graphs slice the data at sane points so that it all can be stitched in a bit perfect way in the modem, so that because the convolutional encoder will get real confused if you don't match things up perfectly, it'll look like an error, right? And you'll lose a frame. So here's just a loopback that's not using hardware, and a neat little thing you can see here. I've got a time series of the modulated data packets. This is just putting random data into packets here. And then this is modulated data plus filler packets. So sometimes I'm not providing enough data and I'm adding a fill frame. And if we zoom in, this is showing 2 full frames here. So if I zoom in here at the right place, you can actually see the ASM between 2 packets. And you can, I don't know if you can see that, but the data over here is changing. The data over here is changing. These are 2 separate frames. But in here, this is the fully encoded ASIM, and that is not changing at all. If you were to look at how we encoded it, it's starting at just the right place. And I think I have some sort of like frame debug here that I got the error counter here I got for free from Andreas, and you can see the frames detected minus frames decoded is hovering around 0. So now let's do this over the air. All right, so I'm going to start up. I've got 2 laptops back here. They're connected up to 2 USERPs. I've got, I think, 60 dB of attenuation in line here between the transmit and the receive, and they're going to be talking on 2 different frequencies. So I'm going to start up this modem, and I'll start up the second modem, and then I'm going to set the IP address for the TUN device on this guy. And I'll set the IP address for the TUN device down here. And if there is a God, I will be able to ping through this thing. How about that? And the really cool thing about it, I've never done correlators with a modem before. Not really needed to, because I've done much simpler things and they've had differential encoding and stuff. But if I disconnect one side of this connection, you'll see the connection die. It should heal right back up. How did that work? Hey, how about that? We're pinging again. So I will kill that. And who likes SSH? The nice thing about IP encapsulation is, you've got an internet link to your spacecraft, and we've got a ton of FEC on this thing because we've got convolutional encoding and Reed-Solomon encoding, which deals with a lot of the issue. IP is not designed to go over the air or deal with lossy links. So let's try that. All right, now we're SSH'd into my other computer over the RF link here, and we can run htop. So we can see fun stuff going over there. And this will effectively end my demo. But I don't know if anyone is familiar with Hollywood, but if you want to screw with your coworkers or make it look like you're hacking, run Hollywood. Apparently, this is made by like a Ubuntu developer, and if you ever see like one of these terrible like crime drama TVs where they're like showing the hacker, or even like in newscasts, you'll often see this in the background, and you'll be like, oh, I know what they're doing. So, what's that? It's a niche conference, right? Okay, cool. And I never know how to exit out of Hollywood, so yeah. So I think we're just gonna kill it there.
All right. Thank you, Dan. If Travis and Robin wouldn't mind coming up to get set up. Oh, perfect. So we have a talk swap. Martin and Travis are swapping places. We have time for maybe one question while we get set up here.
Yeah, sure.
Right here.
Yeah, no problem. Thank you.
Sorry, I was just curious. What was the phase ambiguity you were noticing in your algorithm? Why was there a phase ambiguity?
There's a phase ambiguity because it's a QPSK modem, and I'm not the best guy to answer this question, but you have 4 symbols, and the costas loop, I'm not doing anything intelligent about checking whether it's locking onto the right rotated version of the ASM. So it can lock in different rotations of the constellation and even symbol inversions. And sorry, I'm just disconnecting some power cables here. In the end, your constellation pattern will look good, but your data will not be decoding. And I think the right way to do this is to actually check, or a good way to do this is to check the decoded ASM symbols and see if it actually matches what you expect. I tried that early on, but I was probably messing something else up. So in the end, adding the second costas loop kind of just gave that to me for free. Does that answer your question?
All right. Thank you very much, Dan.
Thanks.
Huh?